In this presentation, we'll examine several different types of internet service along with the features and benefits of each type. And we'll begin with what is rapidly becoming the most common type, which uses fiber optic connections to provide a very fast and reliable connection that can offer download speeds ranging from 25 megabits per second to well into the gigabits per second range, depending on your provider and the type of service you choose. At the time of this recording, I would say that something around 1 gigabit per second is likely the most common type of service, but again, it really depends on the provider. Fiber optics can also be configured in a fairly synchronous manner, meaning that upload speeds are comparable to download speeds, ranging from 5 up to 880 megabits per second at the time of this recording, again, depending on the provider and the service level. Most providers will also bundle your TV and your landline phone service along with the internet so that all services come in over a single cable. As for some of the key features, a specific modem or gateway is required as the central connection point between you and the ISP, but this is something that they would provide as part of your package, and virtually all types of internet service require some kind of gateway. So this is hardly unique to fiber, but because it uses beams of light to transmit data, it is considerably faster and more reliable than either of its predecessors such as cable or DSL, which by the way we'll discuss in just a moment. And regardless of the speed of your service, as mentioned, it typically offers similar upload and download speeds. Now, for most people, most of the time, downloads are more important, such as when you're streaming a movie. But these days, many of us make extensive use of applications such as video conferencing or maybe voice over IP phone calls, which effectively require the same speed in both directions because you're transmitting as much as you're receiving. So a synchronous service is better suited to those types of applications. All of that makes fiber an ideal choice for when performing a lot of file sharing, streaming, or sending very large files such as backups to cloud storage services. And due to its asynchronous nature, services that require real-time communications, such as voice over IP calls and video conferencing, will perform much better. And it also provides the capacity for high-performance server hosting for environments such as web hosting companies and many other types of robust cloud services. In short, if you're looking to implement a new internet service for any reason, these days you would almost certainly want to go with fiber, but it can still be more expensive, and some providers in some areas may still not offer fiber as an option. So, if fiber in fact is not available, or if it's still too expensive, other options include cable internet, which is likely still fairly prevalent in many areas. It uses standard coaxial cable, or the same type of cable that was typically used to connect a TV to its receiver. Speeds can certainly be adequate by today's standards, ranging from 20 megabits per second to 1 gigabit per second on the download side, but cable was almost never implemented in a synchronous fashion, so upload speeds were typically quite slow by comparison, ranging from 5 to maybe 100 megabits per second. Again, all of that is going to be dependent on the provider and the service level you choose. And since it used the same cable as your TV, most providers would combine your internet and TV services. As for benefits, cable is still suitable for many of the same applications as fiber, such as file sharing, streaming, and backing up data to the cloud. And it would still be suitable for services such as voice over IP calls and even video conferencing, just not to the degree of fiber. So to put that in very general terms, if you needed to support all of those applications for an entire network, then you would almost certainly need fiber. But they would run in an acceptable manner for a home or a small office environment using cable. Overall, download speeds are typically good, but the upload speeds would be moderate at best. The main counterpart to cable internet is DSL, which stands for Digital Subscriber Line, which was among the first methods of high-speed internet, but both cable and DSL were prevalent around the same time. In fact, they were engaged in a bit of a battle, if you will, not unlike HD, DVD, and Blu-ray. As always, each with their pros and cons, but in terms of implementation, DSL used existing copper phone lines, so of course one immediate benefit was that the infrastructure was pretty much in place almost everywhere. Although the same could largely be said about cable, but DSL was maybe a little more common. But in terms of the speed, the download side offers a range between 1 and 500 megabits per second, and this would probably be about the max available, so it typically doesn't reach the speeds of cable. And on the upload side, again, it was typically much slower, ranging from only 384 kilobits per second up to about 10 megabits per second. But depending on the provider, you could request DSL service in a synchronous configuration if, for example, you did need to support applications such as video conferencing. So the standard configuration, where most of the speed is on the download side, was referred to as asynchronous DSL or ADSL. And if you needed it to be more or less synchronous, that was referred to as SDSL. But whatever your total bandwidth was, that value itself didn't change. You simply adjusted the percentage of total bandwidth allocated to each direction. So, for example, if it was divided, let's say 90% down and 10% up, you could change it to 50-50, but the increase to your upload speed came at the expense of your download speed. And since DSL used existing phone lines, of course, it was usually bundled with your standard phone service. As for primary features, in its original implementation, DSL was configured as an on-demand service, meaning that you had to establish a connection to your ISP first before you had any access to the internet, which was effectively the same thing that you had to do back in the days of using traditional dial-up modems. Now, that wasn't such a big deal at the time, but with so many of today's applications being connected all the time in the background, checking for updates or refreshing data in near real time, this wouldn't be ideal. Now, two things about that. First, once you did connect, there was really nothing that required you to disconnect. In other words, you could leave the connection active for as long as you like, but some people like the option to be able to disconnect when not in use. And even though the connection used your standard phone lines, it was configured in a way so that using the internet did not tie up your phone line. In other words, you could be online and make phone calls at the same time, which actually was not the case back in the days of modems, unless you installed a completely separate phone line for the modem. Secondly, later implementations did use a dedicated router provided by the ISP, which maintained a persistent connection so that multiple systems could share that connection, either wired directly to the router or over Wi-Fi. So from that point, the connection was always on, just as it was with cable. But as mentioned, since the provider infrastructure was effectively already in place almost globally, DSL was very commonly implemented as a service, but the service offerings were always a function of which provider you went with and the quality of their infrastructure. Typically, very large, very well-established providers would offer the highest level of service, but of course at a higher cost. So it usually came down to what was most important to you, cost or performance. As for merits, DSL is fairly similar to cable in that it is still suitable for light to moderate file sharing, streaming, and backing up to the cloud if you had higher levels of download speeds. But backing up data to the cloud, for example, would be slower than cable unless you had a more synchronous configuration, which also applies to applications such as voice over IP calls and video conferencing. In its asynchronous state, these applications likely wouldn't perform very well, but in a more synchronous configuration, they would perform much better. And overall, the download speeds were fast at the higher levels of service, but not to the degree of cable or fiber. Also of note, DSL tended to maintain its level of performance better when there was a lot of activity. By comparison, cable was a shared service, so the more people that were online at the same time, the slower the service tended to be. So for example, in the evenings when everyone is home, cable could become noticeably slower, but it still had faster speeds overall than DSL. As mentioned earlier, both cable and DSL are being rapidly replaced by fiber, but depending on your region, fiber may not yet be an option, so it's still quite likely that you'll encounter either cable or DSL even today. Now, for those of us with smartphones, of course, standard cellular service also provides us with access to the internet. So as soon as you sign up with any cellular network provider, you immediately have access to the internet using your mobile phone. The term cellular draws from the fact that any given transmission tower, of course, has a limited range. So the range that can be adequately covered by any given tower is referred to as a cell. So the provider's network as a whole would be comprised of many cells that each overlap a little bit with its neighboring cells to ensure that you can move from cell to cell with no disruption of service. But in terms of that service itself, it's all just data. Of course, we refer to it as voice and data, but the voice signals are all digital these days as well, simply meaning that you don't have to do anything to change from one type of service to another. As long as your mobile device has service, then you always have both voice and internet available to you, simply by launching the appropriate app. Other benefits include the fact that cellular network coverage these days is available just about worldwide, at least in most populated regions, but it can still be difficult to get a signal in very rural or isolated areas, and most providers now offer service levels that are on par with even fiber optics in terms of speed. For example, 5G service is capable of gigabit per second speeds, so very much faster than what standard copper wire phone lines can support. So then, for those areas that are remote or otherwise very difficult to reach using something like cellular, satellite may be a viable option and, in fact, is generally the only option for situations such as an oil drilling platform or research or naval vessels that spend most, if not all, of their time out to sea. Now, that's not the only example. You could still be on land, but just in a very isolated area where standard landlines or cellular service just aren't viable options. Key features of satellite internet include only marginally acceptable performance by today's standards, again depending on the provider and the service level, but speeds typically range from about 1 to 100 megabits per second on the download side, but only about 1 to 4 megabits per second on the upload side. And of course, due to the nature of the infrastructure required, the service is typically leased monthly and can be quite expensive. Plus, a satellite dish is required at your location, and since communications are taking place with satellites in Earth orbit, latency or delay between transmission time and reception is often an issue, and that distance simply results in service that isn't as fast as most other types, but again, in some cases, it really is the only option for connectivity. So while it does have its merits, they're certainly more limited as compared to most other services, but of note, it is available to any organization that simply has no other option for any kind of land-based service or one that is beyond the capabilities of cellular. And the speeds are still suitable for applications such as voice over IP calls or even video conferencing if used sparingly. But you can expect a reasonable delay between the time that you say anything and the time it gets received on the other end. But its primary merit is truly global coverage. There is literally nowhere on Earth that a satellite signal cannot reach. Finally, the Wireless Internet Service Provider, or WISP, is our last type of connection, which uses wireless technologies to provide internet access, which is also sometimes referred to as long-range wireless. And if that sounds rather similar to Wi-Fi, that's because that's exactly what it is, just over a much larger coverage area than what standard Wi-Fi can handle. Now, in that regard, I'm not talking about a large environment such as an airport terminal, rather an entire community or even a city. WISP providers can generally use existing infrastructure such as transmission towers to simply carry standard 802.11 based internet over a much larger area, giving them the means to provide internet access in a relatively inexpensive manner because little or no new infrastructure needs to be implemented. Once configured, anyone within range is able to connect and have access to the internet. Now, as a user, you may have to create an account, which might be pay-as-you-go or could be unlimited use for a flat rate, or in some cases, it might even be free. In fact, a city about 4 hours from where I live here in Eastern Canada offers WISP services free of charge. but it's not the highest performing service available, and it is also a public implementation, so it's not secure. But it's certainly good for situations where there is no other Wi-Fi available. Anyway, WISP is not an overly common implementation, but it is a viable option for smaller or remote towns that just don't have a lot of infrastructure in place, so it provides universal access for anyone within range. Ultimately, there are a lot of methods available for connecting to the internet, and like most things, the decision as to which type to use really just comes down to your needs. But these days, there is a means to provide access for just about any situation. In this presentation, we'll take a look at the various different types and classifications of networks that can be implemented, beginning with the local area network, or LAN. Now, for anyone who might work in an office environment, this is essentially what you're working on all of the time. It's probably the most common type of network, and in reality, it can exist anywhere, not just an office environment. In fact, I'd say that it's likely that many of you have a LAN set up within your own home these days as well. If you have at least 2 computing devices that are connected to each other, then you effectively have a LAN. But the overall functionality of a LAN is to allow interconnected devices to share their resources with each other, such as files, printers, and storage devices, and of course for client computers to connect to servers to access email, intranet sites, databases, or anything else that might be available. In terms of communications, LANs use a private IP addressing scheme, which means that the addressing scheme that I might use on my LAN could be exactly the same as the addressing scheme on your LAN, without any concern for duplicate addresses or interference, because all communication on my LAN and on yours stays within your network. In other words, it does not extend to the public internet. So 2 offices side by side could both have the exact same addresses on their respective devices without issue. Each LAN is its own separate network. Individual devices on the LAN are connected to each other via switches, which themselves can be connected to each other to ensure that every device can communicate with every other device. And LANs, partly due to their isolation from the rest of the internet, typically provide very fast data transmissions, and in most cases are fairly easy to design and maintain. For example, you could just take a single switch and plug in 2, 3, 5, or 10 computers to that switch, and they would instantly all be able to communicate with each other. A wide area network, or a WAN, provides network coverage over very large geographic areas, such as connectivity between many branch locations of a major enterprise, all of the campuses of a university, military bases, or any other environment that has many locations that are very distant from each other. WANs do support what is generally considered to be high-speed transmissions, but it depends on the type of connectivity being used. But while still fast, for the most part, WANs are usually not as fast as LANs. WANs tend to require specific hardware, protocols, and more advanced configurations, so they can be much more expensive to implement and maintain. But that also comes down to topology, because there are 2 main types, the switched WAN and the point-to-point WAN. The switched is similar in concept to a LAN, whereby there are many different locations that all have to be connected to each other, much like there are many individual devices plugged into a switch that all need to communicate with each other. And the point-to-point WAN would be appropriate for when there are only 2 locations with a single dedicated connection between each one. So, since it is using just a single connection, a point-to-point WAN would be cheaper and easier to implement, but of course it simply depends on your needs. Large-scale switched WANs can be considerably more challenging to design and maintain, and almost every WAN can be more challenging to design and maintain than a LAN. Now, a MAN, or the Metropolitan Area Network, would fall somewhere in between the LAN and the WAN. In other words, the coverage area would be larger than a LAN, but not quite as large as a WAN. MANs are typically implemented to cover a more specific geographic region, such as within a single city, or even a few blocks within the city. For example, you might see all of the hospitals in a city connected by a MAN, They typically support high-speed connectivity, but they can be fairly hard to design and maintain because MANs are usually implemented internally, so that you have to look after everything. Now, to qualify that statement, if we go back to the WAN for a moment, many WANs are implemented by leasing infrastructure and equipment from telecommunications providers, which means that it's up to the provider to maintain that infrastructure. So, as a customer, I don't have to worry about repairing downed lines or upgrading equipment. But MANs tend to require that the parties involved purchase, implement, and maintain all of the equipment on their own, again making them more difficult to work with, and due to the cost involved, many MAN configurations don't have any redundancy built in because it's just too expensive. So MANs also tend to be less fault tolerant than their WAN counterparts. Next is the Wireless Local Area Network, or WLAN, which of course provides wireless connectivity for our devices using high-frequency radio waves in the 2.4 GHz or the 5 GHz transmission bands. Now, if this sounds familiar, that's because this is what almost all of us simply refer to as Wi-Fi these days, and standard home Wi-Fi does count as a WLAN. And of course, WLANs generally provide us with internet access as well, but certainly its most convenient feature is the mobility it provides. As long as users remain within range of their access point, they can move about and still be connected to the network. Now, just to go into a little more detail with respect to WLANs, while even a Wi-Fi router in your home does count as a WLAN as mentioned, the term itself is generally used more so when referring to larger implementations, such as what you might find in an office building, a hotel, or an airport, or anywhere else where a single Wi-Fi router simply would not be able to provide adequate coverage. So, to provide that additional coverage, there are many different access points spread throughout the coverage area, and they can really be thought of as wireless switches. In other words, any given access point itself is not the device that provides you with routing capabilities such as getting to the internet. Rather, they simply provide you with connectivity to the network overall, just like standard switches do. The wireless access points themselves are likely wired to each other and to the router. They just also happen to allow wireless devices to connect to them. So, in this particular configuration of a WLAN, the router itself doesn't even have to be wireless. The access points simply allow the incoming connections from wireless devices and then allow them to access the rest of the network, which could otherwise be entirely wired. So a WLAN implementation does not have to be only wireless connections. But as always, it depends on the implementation. So both your regular Wi-Fi at home and the Wi-Fi in a very large airport terminal do both qualify as WLANs. And ultimately, every WLAN is still a LAN, it just adds the wireless component. The Personal Area Network, or PAN, refers to a network that is specific to an individual, which usually includes a mix of devices that can be managed from one computer or device, but they can typically be accessed by any device that is capable of connecting. Now, there are different varieties of PANs these days, but perhaps the most common is with Bluetooth devices. So with respect to the central management device, this might be your laptop or your tablet or even your mobile phone. But as soon as you start to connect peripheral devices to that central device, you're creating a PAN. For example, at this very moment, my mobile phone has Bluetooth connections set up with a wireless speaker, a fitness monitor, a printer, and my car. They aren't all active at this very moment, but as long as even one of those connections is active, you have a functioning PAN. Lastly, we have the Storage Area Network, or the SAN, which is a dedicated high-speed network used exclusively for accessing large volumes of high-performance storage over networked connections, as opposed to storage that is installed locally into a server, such as a local hard drive. So, unlike all other types of networks covered so far, SANs are not used for standard users to share resources or access the internet or even to connect computers or offices together. They're used exclusively for network servers to access storage through specific and dedicated hardware protocols and topologies, allowing for exceptionally large amounts of storage to be allocated and managed by the various servers connecting to the SAN. Imagine something like an entire closet or a storage room that is filled with nothing but hard drives. There could be hundreds or even thousands of them. Clearly, there would be no way to install all of those drives locally into a single server. So SAN allow all of those drives to be accessed as a single, very large amount of storage that can be divided up at what's known as the block level, meaning that there really is no distinction between one physical drive and another. It's just all added up, and it can then be divided among your servers by allocating chunks or blocks of storage. And if any particular block happens to span from one physical drive to another, that's perfectly fine. But once the storage has been allocated to any given server, as far as that server is concerned, the storage appears to be local to that host. So it accesses it like any other hard drive. Folders and files can be created on the local operating system, which can then be shared out to the standard clients on the LAN so that they can access those resources just like they would in any other client-server configuration. In the most robust configurations, SANs can even span multiple sites so that if one site goes down, access to storage services can still remain available in the other site. But in short, a SAN decouples the storage from the local servers so that any given server doesn't even need traditional local storage at all. In this presentation, we'll examine some common tools used by computing and networking technicians, including crimpers and cable strippers, which I should point out are not all that commonly used in most environments in day-to-day operations, but they would be essential for anyone who works as a network installer or anyone who works for any kind of cabling company. So beginning with the crimper, this is a tool that in many cases could actually be considered to be a multi-tool because most models allow you to strip, align, and cut cables. But its primary function is to attach the connector of a cable to the bare wire so that it can be plugged into the appropriate interface. So looking at a specific example of an Ethernet cable, of course, cables can be purchased in predetermined lengths with the connectors already in place. But when you're running wire for a new network, such as in a newly constructed building, you would almost always be using what's typically referred to as bulk wire, which is just a very large spool of continuous wire. As an installer, you simply cut off as much as you need for any given run, but that leaves you with a cable with no connectors on either end. So crimping begins with stripping back the protective plastic cable jacket to expose each of the individual wires, which can then be placed into a specific slot in the crimping device, which aligns them accordingly based on the connector, which in this case for an Ethernet cable is an RJ45 connector. Then you simply insert the connector itself into the tool and effectively squeeze or crimp it all together. Again, specifically for an Ethernet cable, the RJ45 connector itself has a very small hinge built into the plastic molding, so it opens up like a suitcase. Inside, it has sharp metal prongs that are designed to pierce the protective jacket of the individual copper wires so that the prongs make contact with the wire. Everything is then held securely in place when you crimp the connector to the cable because the crimper closes over the connector and small tabs lock it all together. Again, that's only one example. Crimpers also exist for many other types of cabling, such as coaxial cable and fiber optic cable. A cable stripper is designed purely to remove the exterior protective jacket of any given cable before it's crimped. The wire has to be stripped first, then placed into the appropriate connector for crimping. But there are many different types of cable strippers available, so it really just depends on the type of cable that you're working with. For example, there are cable strippers that are specifically designed for working with electrical cabling, but they would not be appropriate for working with Ethernet cable and vice versa. And as just mentioned, many crimpers may have a cable stripper built in, but some may only be crimpers, in which case you need the cable stripper as well. In other cases, sometimes you only need to strip off the jacket, but no crimping is performed. For example, if you're working with speaker wire, where bare wire simply gets clamped into a receptacle in the back of the speaker. Regardless, when working with cables, it will simply come down to the type of cable you're working with, and if connectors need to be crimped, then one way or another you'll need a crimper. But even if the crimper has a built-in cable stripper, sometimes using the dedicated tool can just be a little easier to work with. But of course, the choice is yours when you purchase. In this video, we'll discuss the use of a Wi-Fi analyzer, which is a tool you can use to help discover problems with your Wi-Fi signals and to optimize the performance by testing various antenna locations and test and/or verify the configuration of your Wi-Fi access point. In short, the analyzer simply captures your wireless signals and records detailed information about the transmissions so that you can analyze the current configuration, then make changes accordingly if necessary. For example, if your access point is transmitting on the 2.4 GHz band, that band isn't actually using exactly that frequency. It covers a total range from about 2.4 GHz up to just shy of 2.5, with several ranges of specific frequencies being gathered together into 14 channels. But that total range from 2.4 to 2.5 GHz is of course only about 100 MHz. So the 14 channels don't divide that 100 MHz equally. In fact, each channel is about 20 MHz wide. So 14 times 20 gives us a total of 280, which of course is too much. So each channel overlaps a little bit with its neighboring channels. But if you start with channel 1, then channels 6 and 11 are far enough apart from each other that they don't overlap at all. So they're good candidates to use for your devices. That said, there could be another Wi-Fi access point very close to you. For example, if you live in an apartment building, there might only be one wall separating your Wi-Fi router from your neighbor's, and you might both be using the same channel configuration. So there could be some interference. So with the Wi-Fi analyzer, you can pick up on all transmissions that are within range and discover details including the channels being used so that maybe you can use different channels and avoid interference. The typical information gathered by a Wi-Fi analyzer would include the network name being used, the frequency band and the specific channels in use, the overall strength of the signal in various locations, the security protocol being used. Now, I should clarify that this would not give you access to information such as the passphrase. Rather, it would just tell you that the signal is protected by something like WPA2 or Wi-Fi Protected Access version 2. And it might also tell you the Wi-Fi standard, such as 802.11n or 802.11ac, along with any other source of noise that is being detected, which could be causing interference with your transmissions. Once gathered, that data can then be used to determine if you need to improve your coverage area by adding access points or by installing boosters. You can ascertain the actual bandwidth and speed users can expect based on the general day-to-day activities. You can decide which type of connectivity might work best for you. For example, maybe switching from the 5 GHz band to the 2.4 GHz band or vice versa, or switching from 802.11n to 11AC or vice versa. And you might be able to determine if the security configuration might be causing problems, such as the protocol being used being incompatible with older devices. But until you actually use a Wi-Fi analyzer, virtually all of that information would be unknown to you, with the possible exception of something like realizing that the signal strength seems to be weaker in area A and stronger in area B, based on only your experience of having a more reliable connection when you're in area B. But a Wi-Fi analyzer will reveal specific data and statistics so that you can determine why that might be. which of course would be invaluable for optimizing your Wi-Fi and getting the most out of your investment. For example, instead of purchasing some kind of a booster or adding access points, you might realize, based on the data, that if you simply move your existing access point to a new location, that the signal strength is satisfactory for everyone. Maybe it was simply being blocked by some kind of obstruction, or perhaps it was too close to a source of interference. As for the tool itself, there are essentially two varieties: hardware-based analyzers and software-based applications. As you might imagine, the hardware-based version would be a self-contained, dedicated tool that can be used on its own without the need for any kind of host device. It might have the capability to connect to a host computer to download the data, but it wouldn't be required for its use. Software-based apps, of course, require a host device such as a laptop, a tablet, or a smartphone, and there are a number of different versions available. Now, this certainly makes them convenient. For example, we almost all have our phones with us most of the time. So if you have an analyzer app on your phone, it would always be available to you. And since they're just software-based applications, they're usually cheaper than dedicated hardware devices and easier to work with. That said, dedicated hardware devices tend to be more accurate. The software-based apps depend entirely on the signal being picked up by the built-in receiver of the host device itself, which would still be adequate and really even practical, because at the end of the day, that's the device that's being used to make the connection to the Wi-Fi signal. But the hardware-based devices would simply be more sensitive and able to ascertain more accurate data. So, in short, for the best analysis, go with hardware-based, but for greater convenience and ease of use, go with software-based. In either case, they're good tools to have, particularly when you need to implement a very robust wireless solution, such as in a hotel or an airport or anywhere else where a very large coverage area is required. In this video, we'll take a look at some other common networking tools, beginning with a tone generator and a probe. These are very useful if you find yourself dealing with wiring that was poorly labeled or possibly not labeled at all, which leaves you unable to determine where a particular cable end is located. For example, most office locations would have some kind of central wiring room where the Ethernet cables all converge into patch panels so that they can all be connected to your switches. But if that central wiring rack is not labeled, then you won't be able to determine where the other end is located. So the tone generator allows you to place a tone, which is really just an electromagnetic signal, onto one end of the cable, which can then be detected on the other end. So the probe then is the counterpart to the tone generator in that it's the device used to pick up on the electromagnetic signal. Once you place it near the data port where that signal is, it will play an actual audio tone indicating that the signal has been found. Now, that might require a little bit of trial and error on your part, but at least you know when you found it, at which point you have identified the other end and you can label it appropriately. Now, this can still be somewhat time-consuming if you have to trace many lines, because each one has to be probed individually. But if you work with a second person, one person in the central wiring room and another person roaming throughout the premises, and stay in communication over a phone call, you can quickly map out most locations. Tone generators can also be used to test for continuity or breaks in a cable, because if the cable is broken or just disconnected at any point along its path, the tone will not reach the other end. A cable tester is used to do exactly as its name indicates, test that a cable provides connectivity from end to end. It also verifies that the cable was wired properly and that each end is correctly crimped to its connector. There may be varying levels of functionality when it comes to cable testers. For example, basic testers will simply send a signal down one end and verify that the signal reaches the other end. In other words, it tests for conductivity or continuity. But for something like an Ethernet cable, where there are in fact 8 smaller wires within the single cable, it can verify that each individual wire is connected appropriately in each connector. In other words, it can ensure that all of the wires terminate in the right place. In either case, it's usually just a matter of plugging each end of the cable into the tester, at which point indicator lights will report on the cable status. More advanced testers may also include functionality from electrical or voltage meters, such as reporting on the resistance of a cable measured in ohms, which should be consistent across all points of a connection. They might also be able to determine the level of signal attenuation, or a measure of how much the signal degrades over longer and longer distances, and possibly the level of noise or interference that is present in the vicinity of your cable runs, which could result in a variety of issues with your network traffic if the interference level is very high. Again, functionality is dependent on the device, and of course you can choose which type best suits your needs when you purchase. But basic testers are good for just quick troubleshooting, whereas advanced testers would provide much more detail, but wouldn't be as quick or as easy. So like anything, it just comes down to your specific needs, and in most cases, it wouldn't hurt to have both. In this video, we'll examine more tools used in computing and networking environments, including the punch-down tool and network taps. So beginning with the punch-down, this is also commonly known as a crone tool, but it's a fairly small hand tool that is used to hardwire network cables to patch panels, punch-down blocks, keystone modules, and surface mount boxes. Now, with respect to what each of those are, we need to address how Ethernet wiring is typically done in most workplace environments first. So, if you think about a fairly standard office with wired connections, you would typically plug your computer into the data port on the wall using an Ethernet cable. And the same would apply for every other office or room. But all of those data ports have cable runs behind them that run through the walls and along the ceiling or maybe even through the floor until they all reach a centralized wiring room, which is where you would install all of your switches. But the cables that end up converging in that room would have originally been run using bulk cable, meaning that they don't have any connectors attached. All of the cable ends in the central wiring room would just be exposed wire. But switches require actual RJ45 connectors to be present on the cable. So you could crimp connectors onto the end of each cable and then plug them directly into the switches, but that doesn't make for a very organized system. Plus, you wouldn't really have any method of labeling each cable other than using a piece of tape or something to indicate the originating location of that cable. So instead, the cables are all connected to what's known as a patch panel, which is quite literally just a panel that from the front side is little more than rows upon rows of what looks exactly like the data ports in each office. It's just a series of receptacles for the RJ45 connectors. But it also gives you a means to label each connection so that you know where the other end is located. So on the back of that panel is where each individual wire of each individual Ethernet cable is attached to the appropriate interface. So this results in having all of your Ethernet cable runs terminate into a single panel in a very neat and organized manner with the ability to label it appropriately. Then to ultimately connect each system to your switches, you simply plug in a short standard Ethernet cable from the patch panel to the switch. So that all said, it's the punch-down tool that is used to press each individual wire into the appropriate connections on the back of each receptacle of the patch panel to make the connection. Now, a punch-down block is similar, but they don't have any receptacles. They're typically used to simply extend the length of a cable run. For example, if some changes have recently been made to your layout and the central wiring room was moved, you could replace the standard patch panel with a punch-down block. The original bare wire connections could be relocated to the punch-down block, so let's just call it on the left-hand side. Then on the right-hand side, there would simply be more bare wire connections where you could punch down new cables, which would then give you the length required to reach the new wiring room. So it's just bare wire connections on either side, if you will, which again allow you to simply extend the length of the cable. A keystone module is the end where the actual data port in the wall is located, but it's on the inside of the wall jack. So if you were to just pull the cover off of the wall jack, you would see a little square box on the inside where the wires are actually connected, but those wires are punched down as well. And a surface mount box is essentially the same thing. It's a data port on a wall. It just isn't recessed into the wall. For example, if you have brick or concrete, you might only be able to mount to the surface. It's the same type of connection as a keystone module though, just mounted on the exterior of the wall as opposed to recessed within it. So to prepare the cable for making the connections, the exterior protective jacket is stripped back maybe about an inch or two, which exposes the 8 individual wires inside. You typically fan out each pair of wires, and recall that Ethernet cable is also known as twisted pair, meaning that each pair of wires is literally twisted around each other. So there are 4 pairs of 2 twisted wires. So do your best to straighten them out so they can more easily be lined up with their respective slots in the connector. Now, I should also mention that the graphic we're seeing here on this slide represents the keystone end, or the back of the wall jack. The connectors on the patch panel have the same type of slots for each wire, but they would all be in a single row of 8 side by side, whereas the keystone end has 2 rows of 4 across from each other. The punch down process is the same, however, for both. Then, to make the actual connections, or what's called terminating the wire, you use your punch down tool to press each wire all the way down into its slot, which then delivers an impact to compress the cable onto a small metal prong that pierces the sheathing of the wire to make contact with the copper core. And at the same time, a small blade on the tool itself cuts off any excess or overhanging wire. Each wire should be pressed straight down with the tool, not on an angle, and you should hear a clicking sound, which is essentially the impact when the wire is fully and correctly seated. From that point, it's always a good idea to inspect each cable to ensure that no extra cable was left overhanging, and verify that each wire is securely in place at the bottom of its slot. If there is any wire or sheathing still protruding from the connector, then just use wire cutters to trim off any excess. Now, the network tap, for starters, is a fortunate acronym because the word tap has the connotation of tapping into something. For example, if you need to run a new plumbing feed in your home, you tap into the existing system with new pipes. But in this case, it also stands for Traffic Access Point, or TAP. So a network tap is a hardware device used to connect to a specific point in a network where data can be accessed for testing or troubleshooting, or monitoring the flow of network traffic between 2 points. A network tap typically has 4 ports, network ports A and B, and monitoring ports A and B. Network traffic comes in to network port A and flows out of network port B for traffic in one direction, and into port B and out of port A for traffic in the other direction. So there is no disruption to the traffic in any way. And then the tap will make copies of all packets and send them out each monitoring port. So monitoring port A makes copies of the traffic coming in over network port A, and monitoring port B makes copies of traffic coming in over network port B. The monitoring ports can then be connected to a device which can analyze the data and generate reports. Now, bear in mind that while the tap itself does not interfere with the regular flow of traffic, you will have to briefly unplug the network cables to attach the tap. Now, clearly it doesn't take long to unplug a few cables and plug them into the tap, but if you're doing so during a very busy time and you're placing the tap along a busy trunk, say between switches or between the switches and your router, you will most certainly interfere with traffic for a few seconds at least. which might not seem like much, but it could easily halt important meetings or video conferences, so it would be best to place your taps during downtime if you can. In this presentation, we'll talk about when to use a loopback plug, which is sometimes also referred to as a loopback adapter. But before I get into anything here, I do want to quickly clarify that if you're talking about IP address configuration, you may sometimes hear people refer to the loopback address, or they might even say the loopback adapter, but in that context, that's a very different thing. The loopback address is just that. It's an actual IP address of 127.0.0.1 that's used for testing and diagnostic purposes to determine the state of the TCP/IP protocol on your actual network interface. But it's entirely a software-based approach. A loopback plug is a physical hardware device that is actually inserted into a physical network port. So with that all said, the device itself is used for testing and diagnosing the physical port to see if there's any problems such as contacts that have become loose or damaged. And I should also say that they aren't used solely for network ports either, although that is probably the most common. But loopback plugs are also available for USB ports, serial, and parallel ports. Now, there is also a distinction that should be made here. Some of you may be familiar with a type of Ethernet cable known as a crossover, which can be used if you need to connect two computers together directly from interface to interface without using a switch. Now, this is due to the way that standard Ethernet cables are wired, in that 4 of the 8 wires internally are used to transmit and 4 are used to receive. But since every physical port is wired the same way, if you attempt to connect two computers together directly with a standard Ethernet cable, which is also known as a straight-through, you end up trying to transmit to the transmitters and receive from receivers, which simply doesn't work. So a crossover cable literally crosses the wires within the cable itself so that you transmit to receivers and receive from transmitters. So again, this is only needed when you are trying to connect a computer directly to another computer. If you're plugging two computers into a switch, you do not need a crossover cable. They will use standard straight-through connections. Anyway, this is not what is happening with a loopback plug. In the loopback, 4 wires just go out a little bit and loop right around and come right back in to the other 4 connections. So in essence, the device transmits to itself and receives from itself. As such, a loopback plug is classified as being both male and female because it serves both purposes. So if that's a little difficult to visualize, here's a diagram of the individual wires in an Ethernet cable. But if we were looking at a standard cable connection, then the 8 wires in total would just extend straight through to the other end of the cable. But in the case of a loopback plug, there are only 4 wires, and each one literally just loops back to make the connection between the transmitting contact and its associated receiving contact. So contact 1 loops back to contact 3, 2 loops to 6, 4 loops to 7, and 5 loops to 8. And that allows you to test the network interface itself to see if there are any issues, because any data output from the transmitters is received as input on the receivers. But if for any reason the data was not received or not transmitted, it would indicate a problem with the physical port itself. Now, I should mention that while a loopback adapter can be purchased for likely only a few dollars, you could also make one yourself quite easily if you're comfortable with stripping and crimping cables. You simply need to follow the diagram as shown here, which you could easily also find online. But if you build one yourself, it's likely just some wire and a plastic RJ45 connector, so the only diagnostic information you could receive is from the interface itself into which the plug is inserted. In other words, the link light. Whenever you plug a standard Ethernet cable into your computer, If there is a connection to another functioning device on the other end, such as a switch, then the link light will illuminate, indicating that you have a successful connection. So plugging in the loopback plug should also illuminate the link light if the port is working correctly. A purchased unit really doesn't tell you all that much more, but it might come with its own indicator lights. So while they don't provide a great amount of detail, loopback adapters can be quite useful if you're trying to run down failed or failing physical ports in patch panels, switches, or just individual network interfaces on computers. So it's certainly a recommended tool for any kind of network cabling technician, general support technician, or really anyone who needs to support physical hardware. Networking tools. We did this by exploring IP addressing, DNS configurations and DHCP implementations, VLANs, VPNs, internet connection types and common network types, cable crimpers, strippers and testers, and tone generators and probes, and Wi-Fi analyzers, punch-down tools, network taps, and loopback plugs. In our next course, we'll move on to explore how to understand basic cable types and their connectors, features, and purposes.